Okay, in today's class, we are going to discuss junction field effect transistor, the concepts. Uh, the patent for junction field effect transistor was filed in the year 1920. It was very old, right? 1920. Okay, and it was conceived in the year 1930. You can see that almost 10 years they took, for the patent to get approved. So, lot of it was very old device. Jfet is not a new device like BJT. BJT came into existence from 1947 onwards. Prior to that, there was a FET concept. FET was introduced in 1920 itself. At that time itself, patent was filed. And very first device you can see that here, the which was filed by the Lilienfeld. That's why this is called as a Lilienfeld transistor, and it's a pictorial diagram. You can see that there is a top is going to be aluminum plate, and below that there is a semiconductor, and there is an ends. You can see that there is a A and B side, where in which charge carriers will move from A to B, and that's controlled by the plate, aluminum plate, which is on top of this. Okay. So, this is the diagram, pictorial diagram presented in the paper patent filed by the Lilienfeld. Okay. Uh, so, this later on this the people have given the shape to that, the field effect transistor, and you can see currently this is what the symmetrical. If you look at cross sectional view of the Jfet, it looks like this. Okay. Earlier it may not be professional, but later on they made it as a very professional way, the junction field effect transistors. Okay. A voltage applied to the metal plate modulated the conductance of the semiconductor under the metal and control the current between the two ohmic contacts. So, that is what we told here. The current movement from A to B is controlled by this the top plate, which is an aluminum type. Okay. So, good semiconductor materials and processing technology were not available at that time. That is what the difficulty during earlier days to manufacture, to fabricate the Jfet in ICs was very difficult till 1950. So, later on the fabrication was made very simple from 1960s onwards, in fact. Okay. The phenomena of modulating conductance of a semiconductor by an electric field applied perpendicular to the surface of a conductor is called field effect. Many times we do not know what is field effect here. Try to understand the meaning of a field effect here. What do you mean by field effect? The phenomena of modulating the conductance of a semiconductor. So, this is the definition. I will just put a quote here. So, this is modulating the conductance of a semiconductor by an electric field applied perpendicular to the surface here. So, here you can see that we are going to apply electric field something like this, perpendicular to this surface. The electric field will be downward, something like this. Okay. So, this is what it controls the charge movement. The conductance within this the semiconductor is varied by just applying electric field to the vertically downwards here. Okay, that is what it is told here. That is called as field effect. This type of transistor has also been called the Uni Junction Transistor to emphasize that only one type of carrier, the majority carrier, is involved in the operation here. All FETs are uni junction only, they are unipolar, only one type majority carriers are responsible for the conduction. We do not have any minority carriers, concept of minority carrier in this Jfet technology here. Okay, let us look into the basic P and Jfet operation. We have another the Jfet, which is MESFET, which is not under the scope of our syllabus, but this is basic Jfet, P and Jfet operation we will cover here. Look at this cross sectional view here. So, this is a simple cross sectional view of a symmetrical device. As you can see, there is a P plus upper layer. This is a gate region, and there is a bottom also, there is a gate region. You are seeing a cross section here. Okay. So, you can imagine a 3D view of this just by extending this. Okay, just like drawing a diagram, extending this, you can make it 3D like this. Okay. Okay, like this. Okay, sorry, I am not good at writing diagram. So, you can make a this kind of 3D shape, and this will get extend the P plus region, extends like this. Okay. Just imagine this is going to be a cross sectional view of a symmetrical device. The N region between two P regions is called as a channel. Where is channel in the diagram? This is a channel. So, you can see here there is an N channel here. There is a N region here between these P plus, this is a P plus and this is a P plus. Between that there is a channel here. This is going to be a channel. This white area what you see where we are showing here movement of electrons here. So, this is nothing but a channel. Okay. So, electrons keep moving within the channel here. Okay. And there are two p regions, you can see that these are the two p region serving like a gate here, and in this channel the majority carriers will move from source terminal to the drain terminal here. So, here one end we have source, left side what you are seeing here source terminal. The word itself conveys meaning. Source means it is a source of electrons in case of n channel device. In case of a p channel device, it is a source of holes. So, it depends on the type of channel we are going to consider. So, this is going to be the n channel p-n junction field effect transistor. So, drain is the point where charge carriers leave the device, source is the point where charge carriers enter the channel. From the external circuit here through this power supply, charge carriers will enter this channel here, and these charges here, electrons we have shown in case of n channel here, these charges moves under the influence of this the electric field which is acting vertically downwards here. So, because of voltage what we apply to the gate which is in vertically downwards, there is an electric field here which is applied like this vertically downward. So, under the influence of this electric field, the conductance within the channel will change, and that will varies that varies the movement of charge carriers here. That means, this what I would like to say here is this: all these electrons which are moving in the channel, they are not free to move, they are controlled by this gate voltage or controlled by the electric field applied between the gate or between the two p regions here. Okay. So, these charges are moving under the influence of this electric field applied vertically downwards. Electric field is also applied upward also, do not imagine only the downward here, electric field also gets applied like this. So, that means these electrons are moving under the influence of this electric field which is acting vertically, vertical direction here. Okay. Next we are going to define what is source, what is drain, that is made clear here. So, majority charge carriers in the channel will move from source to drain, that is point, this point is clear here, the source to drain terminals. And look at the definition of source here, this is a source which I want to highlight here. Source is a terminal from which carriers enter the channel from the external circuit. So, external circuit already told you, this is the external circuit. So, there are two voltages which you are seeing here, one is gate source voltage, other one is drain source voltage. So, now gate source voltage will create an electric field here, and drain source voltage is responsible for the, it is a force that will move the electron from source terminal to the drain terminal here. Okay, you can see there is a positive terminal is connected to the drain, negative terminal is connected to the source. So, that means the negative terminal is a source of electron. So, electron starts moving like this from negative terminal all the way to the source, electron keep moving like this. Okay, so, this is the electron direction I am showing here. The current direction will be the opposite of this. Now, electrons enters into this the channel region. Now, based on this gate voltage, I have not talked about gate voltage VGS. Later on we will explain what voltage gate to source voltage I need to apply to enhance this the movement of charge carriers within the channel here. Okay. So, this drain source voltage creates attracts the electron from source to the drain here. And here, by the way, there are two electric fields, even though we say that there is a vertical electric field due to the gate voltage, and there is a electric field due to the drain source voltage also. It is something like this. Vertical electric field is like this due to the gate source voltage. Okay. So, it is acting on the channel. At the bottom also there is a gate, right. So, it is acting on the channel something like this. And there is a one horizontal electric field also because of this VDS. You can see that this is an electric field which is acting horizontally also. Okay. This is the direction of the field here. Understood this? Okay. In fact, this field direction will be opposite here. I have showed you wrong direction here. Okay, this is not the direction of the field. I would like to show the field is acting from n side, p side to n side like this. So, this is the direction of field in horizontal direction. So, there are two electric fields now. You know that for what purpose these two electric fields are required. So, this is a vertical electric field, and this is a horizontal electric field. Always when you apply a voltage, it creates an electric field, horizontal electric field, and this horizontal electric field is due to the VDS, drain source voltage, and vertical electric field is due to the gate source voltage. Now see here, okay, both are acting on the channel now, vertical and horizontal electric field, and each field, electric field, has got some purpose here. Vertical electric field varies the conductance in the channel in this region, whereas horizontal electric field, okay, it creates the motion of this charge carriers here. Okay, so electrons will be moving here from source to the drain due to the electric field that exists horizontally here. Okay, I hope you understood this, the movement within the this channel region here. So we explained what is the source terminal from which carriers enter the channel from external circuit, and drain is the terminal, okay, where you can see the carriers leave the channel, okay, leave the device, carriers leave, or it will be drained from the device. So that is the definition of a drain. So now we have defined what is source, what is drain, what do we mean by channel, what is a gate. Gate is nothing but it is a control terminal, right? So gate is nothing but which is a control. So this acts like a control terminal. Okay, so all these terminals you are aware now for what purpose and their importance here. The gate terminal, that there are two gate terminals here. These two are connected together because having two gates is not good. Can you tell me a reason why it is not good having two gates? Any idea? Just think of, I will pose a question here to all of you. We have short circuited this, the two gates together. What happens if I maintain two gates, let us say gate 1 and gate 2? Okay, it becomes difficult for us to control, right? Okay. If you have a one control, it is always good. Having two controls, it becomes difficult. It becomes a conflict. So that's why. So always we will short circuit these two gate terminals and make a common gate, single gate here. So that's what it is mentioned here, single gate connection here. But there are devices you will see. Maybe if you look into the subjects like VLSI design, there we will discuss even another gate called as a back gate, and you will know the importance of the disadvantages of the back gate. But here right now we only consider one gate, single gate. We will not talk about here two gates, okay, for FET. But in fact, FET is a 4-terminal device, but you are seeing here 3-terminal. One is normally this is short circuited here. Okay, there is source terminal, drain terminal, and gate, only one gate because of short circuit. Otherwise, MOSFET is a 4-terminal device. Since majority carrier electrons are primarily involved in the conduction in this channel transistor, the Jfet is a majority carrier device. So, in order to give this Jfet as a majority carrier device, we have justified this this reason here. Okay. Another way you can see that this is regarding the P channel. How do we make a P channel device? So far you have seen N channel, but how do we make the P channel Jfet? Just everything is reverse. Okay, so wherever you see here P channel, this P plus becomes an N plus. Instead of this, if you make an N plus gate, and this also becomes an N plus, and if channel becomes a P, so the complete device is called as a P channel Jfet here. And even currents and voltages, they get reversed in P channel Jfet. So that is mentioned in this point here. Okay, a complementary P channel Jfet also can be fabricated in which the P and N regions are reversed from those of the N channel device. Holes will flow in the P channel between the source and drain. The source terminal will now be source of holes. Okay, now holes are pumped through the the source. The current direction and voltage polarities in the P channel Jfet are reverse of those in the N channel device. Okay, so the P channel Jfet is generally low frequency device. Do you know why we call this as a P channel? We do not discuss this P channel most of the times because of this reason. It is a low frequency device. What do you mean by low frequency device? Compared to N channel Jfet here, because it is given reason you can see here, due to the lower hole mobility. This is the problem with the p type of devices. If you see mobility of electron, mobility of holes, which one is greater? Just look at the concepts of the physics, electron mobility and hole mobility. That's main responsible choosing n channel Jfet and p channel Jfet. So always in any device, the mobility of electron will be larger than the mobility of holes. Roughly, I would say that the electron mobility is 2 times the hole mobility. Roughly, I can say that. Okay. So the electrons are moving at higher speed compared to the holes. So that's why p channel Jfets are not preferred, because they are low frequency device. Due to the lower hole mobility, we don't use them in applications. We use commonly the n channel Jfets. Okay. With that, I will stop here. Next class, I would like to continue this n channel Jfet operation, and let us plot the voltage versus current characteristics from the basic PN Jfet operations here. Okay. So, I will stop at this point and continue next class.